Welcome back. And here we go. Looking at a roadmap. I made it look more like your test roadmaps. And hopefully this will be helpful for you to study. I put a blank version of it on the previous page of these notes, so you can print that off and use it for practice. We're going to give reagents A through G and products Z through O. Where do we even start? Oh, we're going to start with benzene. No surprise there. Let's go A, B, C, D. How do you get these two groups onto benzene? So on the test, you don't have to copy out the roadmap. Just give me A. And what's going on? I have to put an amino group meta to a sulfonic acid. Remember, the amino group starts as what? We do not know how to put an amino group directly on benzene yet. We will be putting amino groups on benzene on multiple occasions on our test. We need to know how to make an NH2 group on benzene. This is about the third time I've said it today. So you need to know the protocol is to first put a nitro on the benzene. You now have nitrobenzene. By choosing to put that group on first, you have to take advantage of the fact that a nitro group is an ortho para-director, keeping in mind that an amino group is, did I say nitro group's an ortho para-director? Oh my God, I should just fire me now. No, a nitro group is the most powerful meta-director, most deactivating group we know. And if I have an NO2 group, which I do, the next group's going meta, and that's what I want. What I was getting ahead of myself on is the fact that we eventually will have to reduce the NO2, which we put on benzene, to this NH2, which is an ortho para director, and you do the reduction first. The next group's going right here for major, which is not what I want, and here for minor, which is also not what I want. So do not reduce the nitro group until you've got the SO3H group on the benzene. So now we've realized we have a multiple step process. Step one. Step two, put the sulfonic acid on the benzene. And that is just H2SO4 and heat. And then step three, you reduce your nitro group to an NH2 group. And that we've been doing, and the safest option is usually the H2 nickel option. So that will give us this desired molecule here, A. Do you want to just continue with A until we run out of things to do with it? Why not? We need to predict what R is. This is the protocol to convert NH2. So step one goes to AR, that's aromatic, N-triple-N. That's called diazotization. The mechanism we're going to learn early on next day when we study amines. It's a mechanism we do a couple times on our next test. So right now you have to know how to do it, and that's the answer to that question. And then what happens to your aromatic compound when you take this and then warm it up with water? And normally the protocol is to just take the ice bath away here because there's water in here now. So step two is really just remove the ice bath, and you're going to get a phenol. I want you to draw a phenol for R. And here's the phenol. It's got where the NH2 used to be, an OH. And the SO3H is unchanged. And what happens to that after I react it? Oh, how do I convert it to this? Oh, that's an ether, isn't it? I've got all the pieces here I need up here except for the carbon. And that's an ether. When I see ethers, I generally start to think about the old Williamson ether synthesis. And that involves making a nucleophilic O-, which is very easy to do with a phenol. What's the pKa of a phenol? 10. That means hydroxide would quantitatively make an O-. So we've taken R and made it into an O- nucleophile. Now we have to react it with a carbon that has a leaving group on this position right there. And that would be like a halogen, maybe a Br attached to a carbon that has a methyl, comes down to a allele group with a methyl there. And that's the end of D. And then what's going on after that? We have to realize that the product we just drew, or sorry, the product up here is an aryl allele ether. Aryl allele connected through oxygen ether. And we can react those with heat. They do react in the presence of heat. Heat's not a reactant, it's a thing. And it's going to cause the Claisen rearrangement. Claisen rearrangement. I don't know. I just had let's try this. And I don't know. That's my attempt at doing a symbol for the Claisen rearrangement, but the N now looks like an R. Okay, that's what's happening. And what happens is you're going to get bonds from the carbon here or the carbon here. They're both ortho to this position here. Remember, in the mechanism, you do the resonance form here to put the pi. In fact, I'm going to just do that for you right now. So you can visualize it better. I don't know what I did there. Visualize it better. Just get my whiteout going here. I don't know how well this is going to work. I'm just going to draw the resonance form here. It's a recipe for disaster, I think, but it doesn't like me erasing everything. Look at those strange dots. I need to look at this resonance form because the other resonance form was good for the other product. We're going to put a group here. It's going to be a bond here to here. You get a carbonyl, and the double bond will end up right there. And so P, and you're going to practice that Claisen rearrangement mechanism. And yeah, it's going to be minor. I'll tell you why in a second. You get a ketone here for a second, but then it tautomerizes to the enol that we call phenol. And the new bond is to the position that used to be the end of the vinyl portion of the allele, the end of that. So it's going to be bonded to a C that has a methyl. A C with a methyl. And it goes to another C with a methyl. And it's a double bond. The arrows go like this. You attack the end position here, and it resonates there, and you get a carbonyl there. Tautomerize to this here, and don't forget the SO3H group, which I almost did, didn't I? That'll be minor because you have nestled that new group between two groups. Steric hindrance is a factor that says doing it up here in this ortho position would be superior. I mean, would involve less steric hindrance is what I'm trying to say. So you're going to put that same group ortho to the hydroxyl on top. Go back to my original resonance form in case you want to practice the mechanism on your own. And the OH is here. And the SO3H is here. Need a little more room to draw my group. The new bond to the same group right there. And the group carbon with methyl, carbon with double bond, E better than Z. And yes, that's E. CH3 out here, CH2 there. And that's Q, major. Less steric hindrance on this side than in the middle of the two groups there. And that is the dead end going that way. I want to go C, then T, and then get to there. Let's try that. How do I get a nitro group para to a bromo? Question is, which one do you want to put on first? If you put the nitro group on first, your next group's going meta. Nitro is the most powerful meta director and the most deactivating group we know. Please don't put the nitro group on first. I don't see a group here or here in the meta positions. Put the bromo on first. That is a ortho para director. So step 1, Br2 and Fe. You've got a bromine on your benzene. How do you put a nitro on the benzene? Once again, that is a pillar of the next test. Putting nitros on benzene. Combination of nitric acid, sulfuric acid, that's C. And let's see, can we visualize the product here? Yep. And then I want to see what happens to, oh, this looks recent. I have a nitro group para to a carbon with a leaving group. I have a strong new. Acetylide is a strong new. So on this page here, and on your page, you'll have at least one addition elimination, probably just one. I don't want you to start thinking addition elimination is more important than electrophilic aromatic substitution, which represents 80% of this page. So, but I don't want you to think it's useless, so I'm going to put it on here. So product T, remember, it's nucleophilic aromatic substitution. What are you substituting for? The leaving group. What's the leaving group? Bromine. Where's the new group go? Carbon with the bromine. It attacks here, resonate up to the nitro, resonate back, and kick off the Br. So your product will look like this. Product T. We'll still have the nitro. Bromo will be gone. In its place, you've got acetylide. Shrink a little. In its place, you've got acetylide. And then how do you get from that? Oh, there's a couple things going on. The nitro is no longer a nitro, and the acetylide became an acetylene attached to benzene, and it became an aldehyde with 2 carbons. There's the 2 carbons. Oh, a little review. It's an A because I didn't relabel it. I made this right before class. So I guess we're going reagents A through H. That should be an H. And what do we have? T, I need to make this thing, which is T, into an NH2. So reagents H. Our favorite reagents H for reducing NO2 to NH2. H2 nickel. And I'm going to say, oh boy, I don't even think I'm going to give you partial credit for that. That will reduce your triple bond. Oh, I told you it was safe, but not always. Yeah, H2PT, H2 nickel. H2 and any transition metal is going to reduce a triple bond from carbon to carbon. I need a reducing agent that's polar, so it won't touch my non-polar alkyne. And our old buddy lithium aluminum hydride is a good one. So now you've got your NH2. Now you have to go back in your memory bank and remember the reaction that converts a terminal alkyne to an aldehyde. And my 241 students, I think they're learning that one today. No, they did it last week. At the end of last week, they learned about HB-Sia2. That puts a hydrogen on the more substituted carbon. That's this carbon here. And a boron on the same side here. And then we have to make an enol from that, which will tautomerize to an aldehyde using our favorites, H2O2 and hydroxide. Hydroboration, and then oxidation, which includes a tautomerization. I don't know if I want to get through the whole roadmap in one segment. Do want to split it up a little so it's not too long, but still too early to stop. So we got to another dead end. Let's get these guys covered. What reagents are going to put an NH2 on the benzene? Well, let's see, we already did that, didn't we? NH2. In reagents A, we put a nitro group on first, and then eventually we reduced it. So put the nitro on, then reduce it to an NH2. And what kind of a group is an NH2? It's an ortho para director. Yay. So I'm not going to do this sequence here. If I did and did my next reaction after the nitro, meta will be the next group. And I don't want meta this time. I want NH2 to be para as the major. In fact, you could even tell me, show off a little bit that you know that would be major, para is major, and with steric hindrance, ortho is minor. I need the NH2 on there first, so we're going to put B right here. Looks a lot like A, but 1 and 3 are done first. HNO3, H2SO4. You've got a nitro group on your benzene. That's an NO2. Step 2, H2 nickel. Now you've got your NH2, which is an ortho para director. And now you're going to put the SO3H group on. And I hope this example illustrates how important the sequence of these things is, because A and B have the exact same reactions, don't they? They have the exact same 3 reactions done in a different order, giving a different result, because an NO2 group is an ortho para director. And sorry, I said it again. NO2 is a meta director. Meta of it's the most meta director we have. And so my next group will go meta. That's A. Yes, I wanted it meta. There's my new group. There's my NO2 group after step 1. It's not an NO2 up here because it's here was NO2 first, then the sulfonic acid, then make the NH2 from the NO2. Down here in sequence B, we put the nitro on, we reduced it to an NH2. So we had NH2 on benzene, and that's a para major director, an ortho minor director, an OP director of the activating variety. So this next sequence would happen a lot faster because the next reaction is with an activator on the benzene. This one had a deactivator. So you might even need a lot of heat here. Should I make that triangle even bigger? With a deactivating nitro on there, you're going to need a lot of heat. And with a activating amino group here, just a little heat. And there you have that. And then we have to figure out what Z is. Z is when you react benzene with an, I don't know if you see it, but that's an acid halide. I'll draw it out for you. That's an acid halide called acetyl chloride. That's this one right here. And that's how you put an acyl group on benzene. So molecule Z has an acetyl group on the benzene. Aluminum chloride is the catalyst we use to put carbon groups on benzene. And we got our acetyl group on there, right there. I didn't draw that very well. Much better. And I want to separate that from beetle. They're real close. There. So that's Z. And we'll pick up Z later. Let's do Y. So I have my acetyl group on the benzene. Oh, yeah, well, there's no chemicals there. So we're up to reagents I. Work in progress. It's worth the wait. I need an I over this arrow. So this is how the sausage is made. You see me making tests up. This is what's going on all the time. A through I. And I, what chemical is going to make the acetyl into an ethyl? Here you can use either the Wolff-Kishner or the Clemmensen. We gave the Clemmensen some love earlier. Let's do the Wolff-Kishner here. OH minus excess AQ, and that always requires heat. And now you've got an ethyl, which is very different than an acetyl, isn't it? And we're going up to Y before we take a break. Going to Y. And we're putting a new group on the benzene, a bromine group. What kind of a director is a carbonyl with its positive natured carbon right here? It is a meta director. I want the bromine to go either here or here. It matters not which. Just make sure you draw one of the meta products. And we got our carbonyl here still. And looks like I have a little more room down here for bromine in the meta position. So that is that. And on the next screen, I'll probably just copy paste everything we need to the left that we haven't done yet. And we'll do that after the break. Sound like a deal? All right. We'll see you then.